This video is to accompany the release of the OpenVentilator.io Spartan Model Mark I crowdsourced and open sourced ventilator project. In this video, I'm going to talk about the OpenVentilator project, about this ventilator, what it does, what it can't do, what we need to do next, and why we built it like we did. In a future video, I'm going to go through some of the engineering details, like what's going on inside of this valve block, and maybe I'll do some disassembly and reassembly. But first, before we get started, I want to make very clear that this is not a medical device. It is not to be used on humans. We are releasing this for the purpose of medical, engineering, scientific, and animal testing. Hopefully some labs will test it out, find any problems if there are some, and give it their seal of approval before it's used on humans. I don't know how I can be more clear. Do not build this machine and use it on humans. It is not for clinical use at this point. This is an engineering prototype. If you are an engineer, a scientist, a lab tester, an animal testing facility, build one, test it, let us know. So usually on my very small and humble YouTube channel, I build things myself and show them in a YouTube video. This time is a little different. This machine behind me was designed by dozens of people all over the world in a crowdsourced project called OpenVentilator.io, link in the description below. It is not entirely my work, although I've been working tirelessly on it, or very tired on it, for the last month and a half or 2 months. But a lot of other people have been, and I would like to give them credit as well. When it became apparent that there was a lack of ventilators worldwide during the COVID-19 crisis, it became apparent to me that we needed a ventilator design that could be built with common parts. I think, and this is just my suspicion, that the reason why we can't ramp up production of things like GE and Medtronic ventilators is not necessarily because we can't get more workforce or scale up factories, but the electromechanical precursor components that are needed to build machines like that are not really available. For example, I celebrate a holiday I like to call Chinese Hanukkah, where you order a lot of electronic parts from AliExpress and they come in 60 days. If you need a pressure sensor and a relay and a valve, you just order a whole bunch of them on AliExpress really cheaply, and then forget about your project, and about 60 days later, every single day for about a month, you get a new piece of electronics in the mail. It's great. Chinese Hanukkah is now operating on like a 4 or 5 month delay, and while most of the components that I order for my projects are not super important, nor are most of my projects, I think this sort of supply chain issue affects precursor components to more complicated digital electronic ventilators. It seemed to me about a month ago that what we needed was a solution that was not the best ventilator that could be made, but a ventilator that would work and would save some lives, but also could be assembled from parts that are readily available almost anywhere. So we built a ventilator that does not use microcontrollers. It does not use ambu-bags or any real medical equipment or electromechanical equipment other than a windshield wiper motor, and basically all of our valves and tubing and materials are commonly available in any place you can find a car. So the next thing I'm going to do is show you the ventilator and tell you what it can do and what it can't do, and what we need to do next, and how you can get involved or help out the project. So this ventilator has the ability to control tidal volume, inspiratory and expiratory timing, both their ratios and the cycles per minute. It also has the ability to control PEEP pressure, which is positive end expiratory pressure. So you can see this balloon is inflating and deflating, but it never fully deflates. That's because it only deflates up until the point where it has the set PEEP pressure. It also has an overpressure control, so that the pump can never break a certain set pressure while pumping into the patient's lungs. Also, the ventilator has an autonomic inhale bypass, so that if you have a patient who, let's say, yawns during the exhale cycle, they can breathe around the machine and still inhale during the exhale cycle. My machine is built out of laser cut acrylic primarily, and a few off-the-shelf nuts and bolts, and some laser cut silicon gaskets inside this compound valve block. There is a machine in the Netherlands that's basically 2x4s screwed together to build most of this pump gantry, and there's 3D printed versions as well. We recognize that all of the pieces are not necessarily medical grade. For example, we're using an inner tube from a truck tire as a bellows instead of an ambu bag. This could be replaced in an industrial manufacturing situation with a silicon cast bellows or even an ambu bag if available. Likewise, there's a few 3D printed parts that are not necessarily medically sound in terms of sterilization, like this little knob over here on the volume setting control. That knob also could be laser cut, injection molded, or just removed, and you could use a pliers to tighten the nut. Also, these ports on the compound valve block are 3D printed just for convenience. You could also use PVC or nylon standard hose fittings that are cut to size, or again, in an industrial setting, you could injection mold them out of any sort of plastic material. So let's take a look at the machine. So you can vary the PEEP pressure by changing the height of this tube. These numbers indicate the number of centimeters below the fluid line level that the end of the tube is sitting at, both for the overpressure tube and for the PEEP tube. And the overpressure tube is always on, and the PEEP is only on during the exhale part of the cycle. Anyway, if we take a look, we're at 9 centimeters of PEEP pressure right now, and the glove does not really fully deflate. If I slide this guy, I gotta put the camera in my mouth for a second. Now we're at about 3 centimeters of PEEP, and we can see that the glove deflates pretty well during the exhale cycle. Pretty low pressure in that glove. Not the best test lung, but it's okay. Also, we can adjust the volume pumped by the pump by changing the crank arm length here. If I shut the machine off for a second. Hang on. You can just loosen this nut, change the length of this arm here. Okay, that's pretty simple. The volume pumped is not so simple as just the area of this piston times the stroke length, because this bellows is not 100% round or regular, and also because the pressure changes within the system, and so that would change induced volume. One of the things we would like to see is you know, an empirical calculation and a chart possibly of pressures in the system and induced patient volumes at peak. One other thing we would like to add is, I'm out of T's, but along the overpressure line we could easily add a T and a U-tube manometer, something like this, so you could read peak pressure in the system, which should be maintained by a check valve on this overpressure line. Let me turn the machine back on. Okay, so over here, pardon my electronics mounting, we have an exhale speed and an inhale speed. We're now, let's say, on the inhale cycle. We can slow that way down, or speed it way up, and the same for the exhale. By changing these two speeds, we can change the ratio of inspiratory versus expiratory timing, and also the total breaths per minute. On this machine, we don't indicate an actual speed or BPM per click on each one of these dials, because the resistance of the lung will also change the motor speed. And so unfortunately, the clinician or lab tester will have to actually use like a chronograph like this watch here to calculate the ratio of cycle times in to out between clicks of this speed switching switch or relay, and one cycle and the next. So this right here is the heart of the machine. This is a flat pack block valve assembly. There's a whole bunch of valves integrated in here, and they do the work of the ventilator. Traditionally, a lot of this work would be digital logic using things like pressure sensors, microcontrollers, and solenoid or other electronic or electromechanical valves. Our solution just uses pressure and a bunch of different interacting valves to accomplish the functions of the ventilator during its cycle. Let's take a look at the ports. This port is gas in. Not in the scope of this project is a Venturi mixing valve that mixes oxygen and intake air. There are other open source and crowdsourced projects working on air and oxygen mixing valves that are 3D printable or injection moldable, and they're reasonably common off-the-shelf medical parts. These two ports are to and from patient. That's these guys going to the T at the glove. This port goes to the overpressure. This port goes to the PEEP system. And this goes to the pump. The pump has another tube down under there, which comes out here. And then this valve system, let's see if I can do this. This valve system is easily removable. Oops. Okay, off. Try not to get my fingers caught. Probably shouldn't do this while the valve is in use. It's got 2 screws, one on each side. And so this valve block can be removed from the machine and disassembled and sterilized, with just an Allen key and maybe a small wrench or even just your fingers, and it can be thrown in, an autoclave or a sterilizing solution. So this valve is a series of laser cut acrylic plates, like these guys. It's a hard one to see. I cut it out of scrap, so we have different colors here. Eventually you have some sheets that have channels and check valve supports in them. And within the block they route the airflow between different ports and do different things. Also we have a series of these silicone gaskets, both for gaskets and, let's see, membranes. Let's see if I have some more over here. So inside the valve block, sometimes we have things like check valves here, right? I don't know that this matches up with this piece, but for example, on a layer like this, you could potentially blow out of a check valve like this, but not suck through. So inside of this valve block system, you have a whole bunch of different check valves and pressure cutoff valves that allow, during the inhale stroke of the patient, for the pump to push air through here, which will then go to patient. Only exit the overpressure if you exceed the overpressure setting. Close off the PEEP system, close off the gas in system, and close off the from patient system. And then in the exhalation cycle, the to patient port is closed. This guy is opened the PEEP is opened. The overpressure won't come into play here because the PEEP is always a lower pressure than the overpressure setting. And then in a separate circuit, gas will flow in and then out to the pump. So the pump is breathing in while the patient is breathing out. We'll take a look at that valve block in schematic later or in another video. Let me turn the machine around so we can take a look at some of my rat's nest wiring. In a production model, these wires would be secured or mostly on a circuit board. This is a windshield wiper motor. It's a Bosch from like a 2016 Jetta all the way back through like a 1955 Beetle. The one in the Netherlands is using a Mercedes Sprinter windshield wiper motor, and you could drill motor mounts to use just about any windshield wiper motor here. Also, there's 15-cent limit switch from a 3D printer here controlling a 5-volt source relay. The Brazilians are using just a bigger switch without the relay. And then the relay switches the motor power from inspiratory to expiratory speed settings. The power is controlled by an ATX power supply. This guy's nice because they're pretty ubiquitous in every computer, every tower case computer in the world. Also, it has a 5-volt out that I can control the relay with, and a 12-volt out that controls the motor. So again, if we look under the machine, I have a lot of rat's nest wiring that eventually should be a circuit board. But you can see here is a ladder of 10A10 diodes, which are commonly available, about 10 cents a piece, or you could even rip them out of a car alternator. And there's 14 of these in a row, and between each of the diodes there is a wire leading out to one of the leads of the 12-position switches that control the speed of the machine in the inspiratory and expiratory cycle. Each one of these 12-position switches has an out to the relay, which then goes to the motor, and then the in goes to some point on that diode ladder to control the voltage going to the motor. So we're not always running at 12 volts, and we can choose inspiratory and expiratory speeds. Over here we have an exhaust module. In an actual build, this module is connected to the top of the sealed PEEP and overpressure chamber, and inside of this tube would be a UVC light that does not produce ozone. It's got a filter on it, and that would just be mounted and caulked into this tube. I don't have that in here because of cash and Amazon shipping, and also I don't have any way to test biological efficacy and the ability to kill virus, but we thought a reasonable way to do it is put bleach in this tank, which cannot be sucked back into the patient because of a check valve system, but it can kill some aerosolized virus coming through the PEEP and overpressure tubes. And then it exits through this tube into a UV sterilization chamber with some sort of the best HEPA filter you can get rubber banded over the bottom of this tube over here. I just have a napkin for display purposes. Again, I have no way here of measuring the efficacy of killing virus in this chamber. Likewise, we would use an identical chamber to feed the machine before the Venturi valve going to the gas in port, again, so that you pull air that has been cleaned into the patient. It's very important that you don't use a UVC light that generates ozone, because that is dangerous to inhale in its own right. Okay, so that's an overview of the machine and what it does, what the settings are. It's very simple. It can be built for about $200, and it can be built, most importantly, more so than the cost, is it can be built with readily available parts. I laser cut mine, but again, you could use boards and a handsaw basically to construct it. It uses an inner tube and a windshield wiper motor, a commonly available switch, a bunch of ubiquitous diodes, really nothing that you couldn't find anywhere in the world. And it doesn't require an ambibag or microcontroller or any electromechanical valves or switches. And I think that's pretty useful in a situation like this. So now you might be asking yourself, what can I do to help? There's a couple of things that the project could really use. First, if you're an engineer, a scientist, a lab technician, if you run an animal testing research facility, we need to test this in a more clinical setting than my 3D printing workshop, or Marcos's backyard in São Paulo, or Joris's basement in the Netherlands. The link is in the description below, and also in the documentation on GitHub. We have a bunch of clinical research questions that we would like answered about the device. If you would like to build your own, please do so and let us know what you find out. Let us know if there are problems with it that you find, or any testing info would be greatly appreciated. If you are an engineer and you would like to contribute to the project, please join our Slack channel. You can read all of the documentation, catch up pretty quickly, and maybe make some suggestions. The project may go forward and create a Mark II or a non-Spartan model that has digital controls and things that are pretty simple that would improve the ventilator, that maybe are not as common as a windshield wiper motor, like an Arduino or electromechanical valves, flow sensors, and pressure sensors. If you have access to a Michigan Instruments test lung, we could use 4 or 5 of them on each of the continents that these things are being built. We would be happy to rent them or borrow them for a while, or if you just wanted to donate one, we would be much appreciative. They're about $2,500 used, and I don't even know how much new. We need a few test lungs and also new view software that comes with the test lungs new to be able to analyze the output of the ventilators. Finally, if you don't have any of these things or are not interested in contributing in that way, cash is always helpful. You can make a donation at OpenVentilator.io, and the money donated is all openly viewable where it goes. The things that we would buy initially are test lungs and possibly more materials for prototyping, either for improving the current prototypes that we have, or building more prototypes to send to labs, scientific research facilities, animal testing facilities. I'll make another video next, and I will disassemble the valve block, so for those of you who are really interested in how it works specifically and what the machine is doing, again, that information is all well documented on the GitHub page in the 5.2.20 release of the OpenVentilator Spartan Model Mark I documentation, but I'll make a quick little video about how this valve block works. I think it's pretty interesting, both in terms of ventilators and just pneumatic engineering, I guess. Okay, thanks very much for watching. I really appreciate it. You have a nice day.